Welcome, my friends. I hope my fellow American citizens either enjoyed or at least survived the elections. But since we don't talk about politics on this channel, let's talk about modern portfolio theory, which was pretty much crazy, insane research already done in the 1950s by Harry Markowitz on a way to optimize your portfolio in a way where, like, you're trying to maximize returns, you're trying to lower your risk. You also take things like correlation among assets into consideration and that sort of thing. This was really cool research by him in the 1950s, and he won a Nobel Prize for it. So I actually wrote a Medium post about this thing. The code will be in this Medium post if you guys need it later, and I'll link it in the description. But for now, we just want to describe the Markowitz portfolio optimization. And then I want to show you step by step how you would find these optimal portfolios with Python. I will appreciate if you guys like and subscribe if you enjoy this video, because it helps YouTube not forget about me. Some of my videos get like no impressions sometimes, so at least give me some. Anyways, let's get started. So basically, the big picture idea of Markowitz portfolio theory is the importance of diversification and the risk-averse assumption. The risk-averse assumption is, let's say you have two portfolios, A and B, and you want to know which portfolio you prefer, A or B. Obviously, if portfolio A has a higher expected return than portfolio B, all else being equal, you would prefer portfolio A. So let's say if you have mu A and mu B as the returns of portfolios A and B, you would prefer portfolio A over portfolio B if just the expected return is bigger. But you have to consider things like risk. And in Markowitz portfolio theory, or modern portfolio theory I should say, risk is quantitated with standard deviation. So basically, if investors to get more return, investors need to be compensated. To take on more risk, investors need to be compensated with a higher return. So basically, if you have to have portfolio A is greater than equal to portfolio B in terms of expected return, this is if and only if its expected risk is also greater or equal to B, meaning you have to take more risk to get a higher return, and vice versa. That's the big picture assumption is investors are risk averse. In practice, I don't know if this is the case, but that's in the theory. Okay, so let me first illustrate the key concepts of modern portfolio theory. The first is the risk-return trade-off. So if you look at this beautiful plot I did here, and I'll explain this in a second, but first, the risk-return trade-off. This basically means that for a given level of return, you have to be willing to take a certain amount of risk. So the higher the return, the higher the risk. So basically, the goal of modern portfolio theory is to maximize returns subject to a given level of risk, or to minimize risk subject to a desired level of returns. It's the equivalent problem. Okay? Another important concept that modern portfolio theory added is the idea of correlation and covariance amongst assets. Like, if you want to diversify and lower your variance and that sort of thing, if your assets are highly correlated, let's say you have Google in your portfolio, then it isn't really diversifying if you just keep them as is. It's much different than like Google and some completely different stock. So the idea of a covariance matrix is very important. So like if you invest in like less correlated assets, you can decrease your unsystemic risk, which is basically risk due to specific investments. But the systemic risk, the market-wide risk, is often undiversifiable, unless, of course, you add to your universe things like safe haven assets. I hate that word, but that. Okay, so now the thing is there's a thing called the efficient frontier. So like I said, for a given level of risk, you want to maximize return. Or the same question is for a given given level of risk, a given level of return, you want to minimize risk. So once you do that, you get a point for each. Let's start with the easier way to assume. For each risk, you want to minimize. You want to maximize the return. So you get a point on the risk return space for each level of risk, and those points are here. They make up the efficient frontier. So let's say I want to maximize subject to, let's say return up to, let's say I want to minimize volatility subject to this return. So the minimum volatility subject to this return will turn out to be, it returns on the y-axis, will turn out to be, let's say 0.3 or whatever. So each of these points represents that optimization, and that's the efficient frontier, okay? And these are not optimal, the ones on the bottom, because these are ones where the best you could do to minimize, maximize return, you have like things above. You only have this top, but the whole curve is called the efficient frontier. Anyways, I don't know why they always have it like this, but these are not optimal because like if you have this volatility and you get negative expected return, why do that when you can get this one? But when you solve the whole thing for each, like you go each level of return, you end up with this curve. But only the top part are the optimal ones. Okay. Anyways, but this is how it's always graphed everywhere. Okay. Okay, so now that we spoke about the efficient frontier, there's one more concept we need to talk about before we start getting into the Python that we're all waiting for. So this is just like you have a portfolio and you have to allocate a portfolio, meaning you have weights and you have to choose like how to allocate your portfolio, like what percent of Tesla, 1% of Rivian, 1% of this, that. But you can also add a risk-free rate, and let's assume in this video it'd be like 0.04. And this risk-free rate has zero volatility and has 0.04 return because it's risk-free. So there's a concept called, first of all, the Sharpe ratio, as you guys know from other videos of mine, is the excess return over the risk-free rate divided by risk. So risk adjusted excess return. So if your return is mu, risk-free rate is r, sigma is the risk, it's mu minus r over sigma. The higher the Sharpe ratio, the better your risk adjusted return is. So it turns out that if you introduce this risk-free rate, you can find the portfolio that maximizes the Sharpe ratio, and this portfolio is going to be here, and this is what's called the market portfolio. It's a portfolio that maximizes the Sharpe ratio. And then you can draw a line from the risk-free portfolio, or just assuming you only own the risk-free rate, to the market portfolio. And this line is called the capital market line. So now the thing is you can have a combination of the market portfolio plus the risk-free portfolio, and anywhere on this line you should be investing now, not on the efficient frontier anymore once you introduce the risk-free rate. Okay. So another thing is if I didn't say this is the maximum Sharpe ratio, another way to get the market portfolio is to draw the line that's tangent to the efficient frontier. And if it's tangent to the efficient frontier, it will intersect at exactly the market portfolio. That's another way to do that. But it's the thing that maximizes the Sharpe ratio. One other geometric thing to see is what is Sharpe ratio? It's the expected return. So it's mu minus r over sigma. So volatility axis is the sigma. So sigma is here. This is mu. This is r. So mu minus r is this thing over sigma. So that's the Sharpe ratio. Yeah, that's the slope of the line is a Sharpe ratio. It's mu minus r over sigma. So remember from for 6th grade, 7th grade, I forget when we learned the slope, it's the y over the x. So it's mu minus r, so this is mu, the optimal mu for the Sharpe ratio, minus the risk-free rate. That's mu minus r over the optimal risk, it's sigma. So mu minus r over sigma, that's the Sharpe ratio. Maybe I'll add that. Okay, so let's hurry up because we're just talking a lot of crap. Let's just define the mathematical formulation, and then let's finally do Python to optimize this damn thing. Okay, so the mathematical formulation, as I said before, there are two things. Right now we're talking about just finding the efficient frontier. So first, let's assume we have our n assets, let's say S1 through Sn, n stocks. Each have a weight, W1 through Wn. And let's restrict the weight to be between 0 and 1, so no short selling and no on margin. And mu is the expected returns for each asset, mu1 through mu(n). Sigma will be an n by n covariance matrix of asset returns. Our target will be just like a parameter, a target expected return. And sigma squared is the portfolio variance, and it's W, the weights transpose covariance matrix times the weights. So let's say your portfolio is n assets of these S1 through Sn, a weighted combination of those assets. So I don't know why I wrote A here. This should be an S. Sorry about that, guys. So this would be Wi times Si. That's your portfolio. That's sum. So if you take the expectation, you get these things. You get weight vector transpose return vector. And the variance, I did this completely wrong. The variance is weight transpose covariance matrix times weight. I will fix that in the medium slide. This is the right thing. Yeah. So here I have a reminder on like mean and variance of sums of random variables, but like you guys can look up a textbook. Basically, let's say you have random variables x1 through xn. The mean expectation of the sum is the sum of expectations, because linearity of expectations can pull out the weight constants and you get this formula. So that's why you can have W1 times mu1 plus W2 times mu2, and that's what you get here. With covariance, variance of the sum, not assuming correlation or anything, is the sum of the variances, sum of the covariances. And when you have Wi xi times Wj xj, you can pull the Wi Wj out. You put the Wj here, and you get W transpose sigma W. So that's the covariance matrix. It's not a math course, so let's move on. So bottom line is you have two formulations. You can either maximize expected return for a given level of risk. So let's maximize this W transpose mu subject to the covariance matrix multiplication. So W transpose sigma W less or equal to your maximum risk target, and then the sum of the weights is 1, because you have to have that accounts for 100% of your portfolio. And the other thing is a similar thing, except now you're not maximizing the expected return. Now you're minimizing the portfolio variance, which is this quantity we spoke about a second ago, W transpose sigma W, minimizing the portfolio variance subject to a specific level of return. So this is the level of return, and we want the weights to sum to 1. I forgot to write that you also want the weights between 0 and 1, so no short selling. Okay, so finally, let's get back to business and show you how to do this in Python. Okay, so finally I have Python. Yay! Okay, so first let's import the packages we'll need. So from yfinance yf, we're gonna, like for most things, we're gonna need pandas and numpy. But the absolutely most important thing we're gonna need is scipy, because we're gonna be using scipy's optimize.minimize to do the heavy lifting for our optimization. Okay, so the thing I wrote here is there is a convention of 252 trading days a year. So like our risk and return, if we just do straight up from daily data, will be daily returns, daily standard deviations. But like the convention is to annualize. So for returns, you can multiply by 252. That's actually a wrong way to do it. And I'll talk about the right way just a little bit in a second. But we'll do the wrong way because it's more common. And for variance, you also multiply by 252. So for so say differently, if you have variance of daily returns, and you want to go to variance of annual variance of returns, you multiply by 252. So so for standard deviation, if you want to go from daily to annual, you'll multiply by square root of 252. Okay, so let's stop with the math and let's show you. So I've had dozens of videos on getting S&P 500 tickers. Let's use as our universe of possible stocks. Let's do a random sample of 1/10 of the S&P 500 tickers. So remember, I have videos with the trick of read HTML, which allows you to like get HTML table, and we'll extract the list of our tickers. I have 500 or so here. Let me now randomly sample 10% of them. So a way you can do that is you can like use the random.sample method. So you can do import random, sample size equals length of tickers, integer divide is these two things, 10. So you can do now tickers equals random.sample tickers sample size. So now our length of our tickers is going to be a lot smaller. It's going to be length tickers equals 50. Okay, so now let's use Yahoo Finance to download the data. So we do, I guess I already imported these things, but we do yf.download, give our tickers a start and end time, and we should get the data. Did I click anything? Okay. So it looks like this. And we only want to use the adjusted close here. Adjusted close adjusts for dividends and stock splits. So I'll do data equals data close. And now to calculate daily returns, you just do something like returns equals data dot percent change. And how does this look? This looks like this thing. So as you see, it always has a nan here, but in theory, if the thing doesn't have all its values or it's a new stock, can have some nans here. So let's drop all of them that have more than one nan. So I'll do that here. I can do something like the drop NA method has a, so I do returns drop NA. Drop NA. It has a thing called threshold. And our threshold will be length of data minus 1. It has to have at least length of data minus 1 non-missing values. Access equals 1. Let's do in place equals true. Does that work? Equals true. And now I'll do, let's see if we have NA still. Ooh. Did I do wrong here? Did I even click this? Oh, sorry. I lost my train of thought. What I did here was I removed the columns with more than one missing value. So now I need to remove that first row that has everything as a missing value. So I need to do returns.drop NA in place equals true. And then this should work. Okay, so now it has no missing values. You can check that by doing is NA.mean, and it should be 0. As you see, 0, no missing values. Okay, so now let's have a function that will compute the average returns, the mean returns. So like I said earlier, is so the mean daily returns is easy. It's just basically all it is just mean returns equals, you have this returns thing and you just take the average. So you do returns dot mean axis equals 1. So mean returns that looks like this. Oops, sorry, wrong axis, equals 0. So basically, for each symbol, you get the mean return, right? What I was saying earlier is that the convention is to annualize. So you would multiply this by a t, the 252, but that's wrong because the percent change is a regular return and not a log return. So what you really should do is you should do this thing. Instead of multiplying by t, but and I have my backtesting metrics video talks about that, but let's use the common convention, which is wrong, to do this. So now we get mean returns. Okay, so similarly we need the covariance matrix annualized. So this is you multiply by trading days to annualize, because it's the covariance matrix, not these square root yet. Okay, so I can do something like cov matrix equals returns dot cov, and then I'm multiplying by t. Again, it would be square root of t if this was a square root, but covariance is like variance size. So this is the annualized covariance. Okay, so finally we can actually try to compute the efficient frontier. So we're going to use scipy.optimize function to do that, and we're going to use the second framework, the minimize portfolio variance for a given expected return. So what we're going to do is we're going to have a given expected return, and then we're going to find the we're going to find the sigma that minimizes it. Okay, so first let's define our objective function, which is portfolio risk, which was, as I said, the sigma or risk that minimizes it. So this objective function is going to be, I'll just call it def portfolio risk weights cov matrix, and then I'll return np dot square root weights dot transpose, and then np dot dot. Sorry, this should be a np dot dot. It's just the covariance formula above. So like, remember the covariance formula? This thing, W transpose sigma W. So let's do that. W transpose sigma is covariance matrix, and then you have to then multiply again by the weights. So it's gonna be like this. So two dot products. It's just the formula I showed above, like that. Okay, so the two dot products are here. So the square root of that, that gives us the risk of the portfolio, or the annualized standard deviation, in other words. So then we can have our objective function of the weights, and then this would just be return portfolio risk weights cov matrix. The cov matrix is fixed, right? So return. Okay, so this is our portfolio risk function, and then we created the objective function, which is just that with the covariance matrix written in. Okay, so now we have to define our constraints. So the first constraint is we want the return to be greater or equal to return target. So so let's first define a def portfolio return. And remember, the portfolio return was this weighted combination of the individual returns. So it would be similar to here, we would have weights, and then we'd have mean returns. Did I call it mean returns? What did I call it? Mean returns, yes. So this would just be, similarly, you just use the formula. So you do return np dot sum. This is dot product, weights times mean returns. Okay, so that's the portfolio return. And we also have a constraint that the sum of the weights equals 1. So let's actually write the constraint as def constraint. Sorry, let's first write this constraint. So constraint ret I should say greater than equal to target return, and equal target return turn out to be the same here. So I'll do constraint return equal target return. So this constraint, so for Scipy, and I'll do a different video on Scipy, your constraints are of this form. Let me show you for a second. Constraints are of the, it's like a list of dictionaries, which looks like this. So our constraints will look like this. You'll have a type, equality, and then you have your function, and you write your function. So let's do the constraint equal to 1 because it's easier. So I'll write def constraint sum to 1 of weights. So you have to either have the form greater than equal 0 or greater than equal to 0. And I'll make a full video on Scipy soon. So this you would return np.sum weights minus 1, because this is what has to equal 0. Okay, and now the other, we can keep it as let's keep it as equal. Sorry, this is hard to explain, so I keep losing my train of thought. Okay, so let's have a constraint return equal to the target return. So okay, so let's have weights, and let's have some target return, and then let's do return portfolio return weights mean returns minus target return. I wish there was a Walmart return, but I guess there's not. And that just okay, so this should be okay. And now I didn't define the target return yet. I'll show you in a second. Now you have to define your parameter bounds. So remember, this is when I said it should be between 0 and 1. I forgot to write that, but like this is so you have no short selling. So bound 0 and 1, length of mean returns is basically the length of the number of assets I have. And then you have to have an initial guess. So let's just make it as even weights for everyone. Okay, so let's do 1 over length of mean returns times. So that's the initial guess. Okay. So now let's optimize the portfolio for one return. Let's say 10%, for example. So let's then write, so let's do target return equals 0.1, and this is what we want to optimize for. So we'll do result equals optimize.minimize. We write our objective function, and then we write our initial guess equals initial guess, and then let's write it. We do constraints equals constraints. You can give a method and that sort of thing. I didn't give a method. I won't give a method here. Bounds equals bounds. Let's see if this worked. So return target is not defined. Okay, so I needed to define it here. Okay, anyways, I needed to define return target here. Return target. What am I doing? Return. Oh, return target, not target return. Sorry. Oh, it might have actually worked if I just wrote return target. Let's see if this works. Okay, that does work. Now let's see if the optimization works. So once you call the optimize.minimize, now what you get is you get the result here. And let's see what it said. Terminated successfully. The optimal return for this, the minimum risk or standard deviation for this return is 0.1. The weights are this X thing. So if I do like result x.x, I think it works. This would be dot shape 50 would be the 50 weight for each asset. And as you see, it'll be dot max would be less than 1, and dot min would be 0, and dot sum would be 1. Okay, so now that's the result. So I'll just rewrite it here. Okay, so now let's optimize. Okay, so this was just one value of the efficient frontier. So of this beautiful curve, this was just one value. I said 10% return. It's this value what we received. Okay, so now we want to optimize for a range of returns. So basically, let's just create a range of returns, which would be, let's say, from the minimum average return to the maximum for each asset, and let's just do 100 such things. And we're going to store this in something called efficient frontier volatility, maybe, or let's make that a list. And then we can have a function called, we don't need a function. We can say, what I call it here, I called it return target. So I can say for return target in target returns. There should be a Walmart returns. I love Walmart. And now let's define this constraint thing here, because we want to, like, you might not need to do it here, but just in case, let me do it. So because then I can have the target return, it'll be here. And then I can define the constraints here. I might not have needed to do this, but just to be a little more organized, so I defined the first constraint, and then all the constraints. But now we're populating return target from here, and these are the constraints. And then we call the optimize function, which is the thing we called above. So let's do that. And then remember our result was dot fun. That's the optimal result. So let's for the efficient frontier volatility dot append result dot opt fun. Sorry. This always doesn't work the first time, so let's see if it works. Oh, I should have printed to see where we're at. The next step is to plot the efficient frontier alone. So if you guys remember how to use matplotlib, maybe I should have I didn't import it. Okay. I'll spare myself the rewriting and copy it from where I have elsewhere. So where are we at right now? We just we're doing this optimization. Did it finish? Oh, it finished. Okay. So let's just plot this. Did it work? So this is just the efficient frontier for our sample of 50 symbols, right? Okay, so now we wanted to add the risk-free asset at 0.04. Risk-free asset, because from the risk-free asset, then as I showed before, you can do the capital market line. So risk-free asset is this thing, and And then we can find the market portfolio. I said it's either the tangent line or the one that maximizes the Sharpe ratio. Let's do the maximum Sharpe ratio because we sampled points and I want to get the exact point. So first, let's just add the risk-free point. So this would just be like, let's assume risk-free rate is 0.04. So I would just do risk-free rate is 0.04. Same exact plot as here. I just copied and pasted everything. The only difference is I'm adding a point 0, x equals 0, and risk-free rate, color is red, to give the risk-free rate point here. Okay, so this added the risk-free rate point. So now let's maximize the Sharpe ratio so we can get the market portfolio here, right? The ratio, of course, measures the excess return relative to risk, excess return over the benchmark risk-free rate relative to risk. But because the package is minimized, so we're going to actually minimize the negative Sharpe ratio, which is the same as maximizing the Sharpe ratio. So first, let's define a function for the for the negative Sharpe ratio. So it'll be this function. It'll be weights. Okay, so so for a given set of weights, when you have your mean returns, right? One second, let me see if I even did this right for a second. Given set of weights times mean returns, that's the portfolio returns, and then volatility is this thing. I actually, you know what? Instead of copying and pasting, I actually have functions that did this earlier, right? I had, remember here I had something that was called portfolio return, and then I had here something that was called portfolio risk. So let's just use those functions. So portfolio return, oh, but it's the same name, so it's not good. Portfolio return, and then what did it take? It took weights and mean returns. Okay. I just copied and pasted this. It might have been a bad idea, so I'll call this portfolio and return, just to make it a different name. Portfolio and volatility, and then I have a thing called portfolio risk. Portfolio risk, weights, and then what else do we need? We need the risk, we need weights, and we need the covariance matrix. So annual return, annual volatility, and let's see, we might not need half these arguments. We do need the risk-free rate. That's all we need, right? Risk-free rate. And then a Sharpe ratio is just portfolio return. So portfolio annual return, I should say. And I should fix these names. And then this risk-free rate divided by portfolio and volatility, and that's the negative Sharpe ratio. So now, similar constraints. I guess the only constraint now is that this weights sum to 1, which is what we had earlier here. So this constraint. So we have constraints sum to 1, but let's copy the constraints here again. So we have this. So again, you write type, equal, and function. That's your constraint. So the only constraint here is it sums to 1. So we don't need the second constraint. And now, what else do we need? Now we just need to optimize. So where's our optimize function? This was where we had this thing. We can use the same initial guess. So I could do, the only difference is our objective function is now the neg Sharpe ratio. And you know, I could do something like, so let me do fun equals this. I don't like doing it this way. There's a thing called args because I have it here. I prefer just having a function or a partial where like I put the argument, but let me show you how you can do it because I need this. We're optimizing the function of weights, but we need to put the risk-free rate somewhere. So I'll show you how you can do it, but I don't like this way because it's buggy later on. So there's a thing called args. So I can do args, and then I can do risk-free rate like that, and then this gives me result. And what does the result give us? It gives us a result that looks like this. Termination successful. Okay, so now from the result, I'm gonna just help myself. The optimal weights is .x, of course. So you know what? Let me help myself because I already did this somewhere else. Okay, so so the weights is the result.x. The market portfolio is just the linear combination of the weights times the mean return, and then the volatility. And let's use the functions we have to calculate these instead. So I have, and I'll fix it. We should call it like get portfolio return. All right, I'll fix it later on to make it a little bit more clear. So portfolio return of that, and then the other one was portfolio risk, because it's better not to like do the same calculation 100 times. But the names get a little annoying because it's easy to get the same name. So weights, covariance matrix, except this is optimal weights. Max Sharpe ratio is the negative of the function because we're minimizing the negative Sharpe ratio. Okay, so now we have our thing, and now let's add that to the plot. First things first is like, let's make a line. So the line will be the capital market line. So remember, what we just did was we found this point here. And you know what? Do you want to see that this point actually works? We can do that for a second. I can do that by, let me just do this. Let's see if this works. Yeah, as you see, this is the market portfolio we just found. So now we need the capital market line, right? So, maybe I'll add that here, just so you guys have step-by-step things. Okay, so now we need to add the capital market line. So this is a line that goes through here, right? So one way to do this is going to be basically to do, we know it has to go through the, so like from basic math that we all forgot, if you from basic math we all forgot, let me just say two things. Okay, so the x-axis, the volatility, we're going to do lin space, meaning we're going to 0 times market volatility times 2. So I'm going to make it to this length. Okay, so that's that. And then the y-axis, to find a point that goes through a point. So it'd be, let's say you want a point that goes through x equals 10 or something, right? So your formula would be like some slope times x minus 10. This is like a line that goes through x equals 10. So that's why you would have the volatility, which is your x-axis, right? That's the x. Anyways, let's just this is, I don't know how to explain it now on zero sleep, but like basically it's a line through these points. You can check my math later, and then you can plot the line to make it like more pretty, because prettiness is useful in plots. And then I added a few optional things like annotations and random portfolios. This is optional, but let me just illustrate a little how I did it. For random portfolios, what I did is I like sampled from a random Dirichlet distribution, because like a random dot random or dot normal random is too concentrated. So random Dirichlet, I got a nice diversity of portfolios. I did some cool things here with np.einsum. I learned a new trick. I'll make a short about it. So anyways, you do that, and then, oh, I already did that actually. So now look up, you get the pretty graph like that. Anyways, sorry I got a little stuck at the end. Hope you enjoyed. Please like, subscribe. Thank you guys so much. Have an amazing day. And again, this is going to be on Median. close this thing. I don't know.